Hello students, we are doing current electricity. Current electricity class 12. Uh, Today's topic is Wheatstone Bridge. Wheatstone Bridge. Wheatstone Bridge is used to find the unknown resistance in a given network. Let us see what is Wheatstone's bridge or what is Wheatstone's network. Principle. Current does not flow between equipotential points. So what is an equipotential point, or what are equipotential points rather? The points between which the potential difference is zero, or the points which are same potential, same electrical potential. Wheatstone's network consists of four resistances R1, R2, R3 and R4, which are connected to form a quadrilateral. So this is the quadrilateral ABCD. Resistance R1 across AB, R2 across BC, R3 across AD and R4 across DC or CD. A source of EMF E is connected between two diagonally opposite points as shown here, and the key is there. The key is on, that means the current is flowing in the circuit. A sensitive galvanometer is connected between the other two diagonally opposite points. I'll show you that. So between B and D, a galvanometer is connected. Due to source E, current starts flowing through all the resistances and in all the branches. So this is the direction of the current. I is coming from the source EMF E. At junction A, I splits into two parts, that is I1 and I2. I1 goes through resistance R1 and I2 goes through resistance R3. At junction B, some part of the current I1 flows through the galvanometer. So some part of I1 enters the galvanometer through the path BD, conducting path BD. So let that current be IG, and now as at B current is distributed, IG flows through BD, so through BC the remaining current I1 minus IG flows. Now at junction D here, I2 and IG they meet and flow together through R4. So I2 plus IG flows through the resistance R4. So you can see from the diagram, from the network, so I2 plus IG flows through the conducting path DC through the resistance R4. At junction C, I1 minus IG, that is the current coming through BC, and current I2 plus IG coming through DC, meet and they combine and flow together as I and return to the same EM source. Current will not flow in branch BD of the network if and only if VB is equal to BD. That means VB, the potential at the point B, electrical potential at the point B, and electrical potential at the point B are same. So there is no potential difference. So VV is equal to VD. As a result of that, no current flows through the galvanometer G, that is IG is equal to 0. If VV is equal to VD, IG is 0. This happens to be true only if R1 by R2 is equal to R3 by I4. So if this is true, then only the potential at B and potential at D is same, and no current flows to the galvanometer, that is IG is equal to 0. So if this expression is true, so this is known as balanced condition of Wheatstone's network or Wheatstone's bridge. Now see, your IG is 0 marked in red and I1, I2. So I1 flows through AB. So I2 flows through AD. So plus and minus are marked here. So now the proof of Wheatstone's bridge principle. So applying KVL to Kirchhoff's voltage law to the loop ABDA. So this loop minus I1 R1. Note the sign convention, plus I2 R3. No current flows through IG, so IG is 0. Minus I1 R1 plus I2 R3 is equal to 0. So this is happening in the loop ABDA, and we are following Kirchhoff's voltage law. Therefore, I1 R1 is equal to I2 R3. So this is equation 1. Now applying KVL to the loop BCDB. So this loop BCDB. I1 R2 plus I2 R4 is equal to 0. This is true because there is no IG. That means no current is flowing through the galvanometer. We have taken IG as 0, so we are neglecting the IG part here, because this is I1 minus IG and this is I2 plus IG. So we have neglected it. That's why I1 is flowing through BC and I2 is flowing through DC. So from this expression we get I1 R2 is equal to I2 R4. This is equation 2. Now I1 R1 again I am writing is equal to I2 R3, equation 1, and I1 R2 is equal to I2 R4. This is equation number 2. Now what I am doing, I am dividing equation 1 by equation 2. So I1 cancels on the left hand side. R1 is equal to R2. Similarly, I2 is cancelled on the right hand side. So we get R3 is equal to R4. So this is the expression. And this is only true if IG is equal to 0. That means VB and VD are same. Balancing condition for Wheatstone's network can be obtained by using Ohm's law as well. Let VA, VB, VC, and VD be the potentials at points A, B, C, and D. Now, we know VB is equal to VD because IG is 0. So minus of VB is equal to minus of VD. Remember, the potential at B and potential at D are same. So I make VA minus VB on the left hand side, and on the right side similarly VA minus VD. So I am adding VA on both sides. So VA minus VB is equal to I1 R1, I1 R1. So VA minus VD is I2 R3. So VA minus VD is I2 R3. This is equation 1. Now again, I'm writing VB is equal to VD. Now what I'm doing, so I am subtracting VC from both sides. VB minus VC is equal to VD minus VC. So VB minus VC is I1 R2. This I1 multiplied by R2, potential difference across B and C is equal to VD minus VC. So I2 R4. So this is equation 2. Therefore, I1 R1 is equal to I2 R3 equation 1 and I1 R2 is equal to I2 R4 equation 2. So again I divide equation 1 by equation 2. So R1 by R2 is equal to R3 by R4. So if I know three resistances, so I can get the fourth unknown resistance from here. Now MCQs. Question of 1. Wheatstone bridge can be used, number 1, to compare two unknown resistances. Number B, to measure small strengths produced in hard metals. C, as the working principle of meter bridge. And D, all of the above. That is A, B, and C. And the correct answer is A, all of the above. So A, B, and C. These 3 points are true for Wheatstone bridge. So Wheatstone bridge can be used in either of the three processes or all of the three processes. Now question 2. Wheatstone bridge is more sensitive when the arms ratio is, this is a very important question. Number A, equal to 1, less than 1, more than 1, or 0. So A is the correct answer. Wheatstone bridge is most sensitive when the arms ratio is equal to 1. Now meter bridge. Application of Wheatstone bridge. This device is a practical application of Wheatstone bridge used for number 1, measuring an unknown resistance, and number 2, verify the law of resistances. Let's have a look at the construction of meter bridge. See, C1, C2, C3, metal strips used for low resistance. Now A and C is connected. So this wire is made of nichrome, manganese, or constantan due to high specific resistance, that is high resistance value. A meter scale is attached. Resistance rheostat RH is used to reduce the current in the network, and the key is there and the EMF E. X is a resistance, R is another resistance. Now the galvanoid is connected and the key is free to move on wire AC. Now this is called the jockey and it can be touched on any part of AC. When key is closed and current is allowed to flow through the circuit, see the current is flowing, current I. So when jockey is touched with the wire AC at point D, so galvanometer will show no deflection. That means the potentials are same. Let that length AD be Lx. So it's a meter, it's a 1 meter long wire. So LR is equal to 100 minus Lx. So Now, by the principle of Wheatstone Bridge, X by R is equal to resistance of the wire AD divided by resistance of the wire DC. Now, sigma is equal to R by L. Sigma is a constant, its resistance per unit length. Therefore, R is equal to sigma L. We have taken it. So, X by R is equal to sigma Lx by sigma 100 minus Lx. So, we equate it. X by R is equal to sigma Lx by sigma 100 minus Lx. Sigma sigma cancels. So, X by R is equal to Lx by 100 minus Lx. So, we know Lx. So, we know R. So, we can calculate X from this relation. X is equal to R multiplied by Lx by 100 minus Lx. Knowing the value of R and Lx, value of X can be calculated easily. Now MCQs. In a meter bridge experiment, when the resistance in gaps are interchanged, the balance point did not shift at all. The ratio resistance must be very large, very small, equal to unity, or zero. Your answer is equal to unity. Now, thank you very much. Don't forget to subscribe this channel and please like it and share it as much as possible.